Hi, in this video, we are going to look at families of curves. So this will be the last topic where we discuss analytic geometry or coordinate geometry. And we are going to cover this theory for family of curves. And then we are going to look at a few questions to show you how to apply the theory. So first of all, we start with the definition. What is a family of curves? So it's a collection of curves which share some common properties, which share some common properties. So we start off with family of straight lines and we look at how we proceed from there. So first topic here is family of straight lines. And the first example that we look at is the family of lines passing through a fixed point, x naught comma y naught. So how would we write the equation of the family of lines passing through a fixed point, x naught comma y naught? So the way to do that is lambda 1 y minus y naught plus lambda 2 x minus x naught equal to 0. Here lambda 1 and lambda 2 are parameters. So lambda 1 and lambda 2 are constants or parameters whose values which we can tinker with, and this is a linear equation in x and y, and it will definitely pass through x naught and y naught. So this must be a straight line. The slope is obviously given in terms of lambda 1 and lambda 2, right? So this is the family of straight lines equation that passes through a fixed point x naught y naught. Let's look at it in a different form. Family of lines that are parallel to a given line. The given line is ax plus by plus c equal to 0 is the equation of the family of straight lines parallel to this given line would be ax plus by plus lambda is equal to 0. Here lambda is not equal to c and lambda is the parameter. So basically we are preserving the slope. Slope here is minus a by b, just like it was minus a by b here, right? Another example is the equation of family of lines perpendicular to a given line, and the given line is ax plus by plus c equal to 0. This equation will be bx minus ay plus lambda is equal to 0. Here we have put it as bx minus ay because the slope here is minus a by b and here the slope will be b by a, right? So that makes it perpendicular because m1, m2 is equal to minus. The next example is when the general forms of two lines L1 and L2 are f1 x comma y equal to 0 and f2 x comma y equal to 0. So think of this as a linear expression in two variables x and y. F1 and F2 definitely represent straight lines, and these are the lines L1 and L2. Then the family of lines lambda 1 f1 xy plus lambda 2 f2 xy equal to 0, where lambda 1 and lambda 2 are parameters. Basically, this equation represents all lines that pass through the intersection of L1 and L2. the intersection point of lines L1 and L2. Why should it pass through the intersection of all lines L1 and L2? Because here L1 equation was F1 and L2 equation was F2. So any point that is the intersection point of L1 and L2 basically makes L1 equal to 0 and makes L2 equal to 0. So definitely that will satisfy this equation, right? So the intersection point always lies on this because it satisfies this equation. And this is in general a straight line, a family of straight lines. So basically it will be the family of straight lines passing through the intersection of L1 and L2, right? The next type of line equation that we will see, fifth type that we will see is family of lines whose x and y intercepts sum up to A. So the sum of the xy intercepts of a line is A, and what is the equation of all the lines that satisfy this property, right? So that family can be written as x by lambda plus y by A minus lambda equal to 1. Here lambda is our parameter. This is the intercept form of a line equation, and you can see that the x-intercept and the y-intercept add up to A, right? And the final family of lines equation that we'll see is the family of lines whose distance to the origin is fixed. Whose distance to the origin is R, and R is greater than 0, right? This type of line family can be written with this equation. X cos theta plus y sin theta is equal to R. Here theta becomes our parameter and R is the distance to the origin of this line. You can easily check with distance formula from 0, 0 to this line, that will come out to be R, right? So that is your family of straight line. Now we'll look at families of conic sections that are generated by straight lines. That are generated by straight lines. So the first example here is this. But before we do that, actually, I will just set up some notation here. So we'll say let fi x comma y equal to ai x plus bi y plus ci, where I is equal to 1, 2, 3, and so on, be the ith line. So this is obviously a line equation. If you say fi(xy) equal to 0, then it will become a line equation. And you can represent multiple lines with this notation. When I is 1, it is the first line. When I is 2, it's the second line, and so on. So now we'll look at this family equation. If the equations of the three sides of a triangle are fi(xy) equal to 0, where I goes from 1, 2, and 3, the equation of the family of conic sections that pass through all the three vertices of the triangle are basically f1xy multiplied by f2xy plus lambda times f2xy multiplied by f3xy plus mu times f3xy multiplied by f1xy equal to 0. Here lambda and mu are parameters. So try to understand what is happening here. We have the three sides of a triangle. If you know the equations of the three sides, the line equations of the three sides, those are our f1, f2, and f3 equal to 0 equations, right? Those are linear equations in x and y. Now, for the triangle, if there is a conic section that passes through all the three vertices of that triangle, the conic section equation will in general be this. So you could have a situation where a circle passes through the three vertices of a triangle, which is basically the circumcircle of the triangle. So the circumcircle of the triangle will have this general equation. Now, after that, you can apply the condition that this general conic is a circle for it to be a circumcircle, and that will be a condition on the x squared coefficient and the y squared coefficient, which have to be equal, and also the coefficient of x, y in the general conic must be equal to 0. However, that is not all. You could represent a parabola that circumscribes a triangle, or an ellipse that circumscribes a triangle, or an hyperbola. So in general, this equation with lambda and mu as parameters represents the circumscribing conic around the three vertices of a triangle, if you know the equations of the sides of the triangle, right? So this is a very useful property. So make sure that you understand this. The next example that we'll see is this one. If the equations of the four sides of a quadrilateral are fi xy equal to 0, where I can be 1, 2, 3, 4, then the equation, so we are doing the same thing, then the equation of the conic section that passes through all the four vertices of the quadrilateral that circumscribes the quadrilateral or passes through all the four vertices of the quadrilateral will be f1xy multiplied by f3xy plus lambda times f2xy multiplied by f4xy equal to 0. Now here, one thing to notice is f1 and f3 are opposite sides of the quadrilateral, and similarly f2 and f4 are opposite sides of the quadrilateral. So if you know the equations of four sides of a quadrilateral, you can find the equation of the circumscribing conic. And that's how we do it. f1, f3 plus lambda times f2, f4 equal to 0, where f1 and f3 are opposite sides of the quadrilateral, and f2 and f4 are also opposite sides of the quadrilateral. The third example is this one. The equation of family of conics that are tangent to two given straight lines. The given straight lines are f1 xy equal to 0 and f2 xy equal to 0 at given points m1 and m2 is, so basically what is the situation? The conic sections that are tangent to two straight lines f1xy and f2xy at given points m1 and m2. So the conic section is tangent to f1 line at m1 and f2 line at m2. So all possible conics that satisfy this condition will be f1xy multiplied by f2xy plus lambda times f3xy multiplied by f3xy equal to 0, where what is this f3xy? f3xy is the equation of the line joining M1 and M2. M1 and M2. So this is the point, this is the equation of the line joining M1, M2, and these are the two lines which are tangent to the conics at the points M1, M2. So this in general, basically F1, F2 plus lambda F3 square equal to 0 is the equation of conics that are always tangent to two given straight lines as two known points. And F3 is the equation of the line joining the known points, right? The next example is this one. The equation of family of conics that pass through the four intersection points of two straight lines f1 xy equal to 0 and f2 xy equal to 0 with a given conic section. Capital F xy equal to 0 is, this is given by f of xy plus lambda times f1 xy multiplied by f2 xy equal to 0. So what is this? This is like saying that we have a given conic section, let's say a circle. This is f of xy equal to 0. And we have two lines that are intersecting the circle, a given conic section at 4 points. So what we want is the equation of all possible conics that satisfy this condition, that basically have 4 intersection points with these two given straight lines. So that will be this equation. Capital Fxy is the equation of the conic itself, and F1 and F2 are the two line equations. So that gives you the family of the conic. So all of these 4 cases where we are looking at equations of families of conic sections that are generated by straight lines are super important in problem solving. So go through them once again and we'll see how it is applied in problems. So you should learn how to apply it in actual questions. We'll look at a new type of family. This is families of circles. Families of circles. So for two circles, where the equations are given by Cixy, it stands for x square plus y square plus dix plus eiy plus fi equal to 0, where I goes from 1 to 2. This is the general equation of two different circles with the subscript indicating which circle it is. If I is equal to 1, it's the first circle. If I is equal to 2, it's the second circle. These circles have different centers. The equation C1xy plus lambda times C2xy equal to 0. What is the meaning of this equation? This is the family of circles that pass through the intersection point of these two circles. Pass through the intersection points of these two circles. Now that is true only if lambda is not equal to -1. If lambda is not equal to -1, you will get this overall equation will be equation of a family of circles that pass through the intersection points of these two circles. If lambda is equal to -1, what you will end up having when you have -1 here, the x square, y square terms will get cancelled and you end up with a equation of a straight line, and that straight line is actually the common chord of the two circles if the circles intersect. If circles intersect, and if the circles don't intersect, that becomes the radical axis of the two circles. If circles don't intersect. So this equation can represent actually multiple things. It can be a family of circles, it can be common chord, or it can be radical axis. Depending on the situation, what is happening, right? Let's look at the next type here. For a given circle, C1xy equal to 0 and a point m comma n on the circle, the equation C1xy plus lambda times x minus m whole square plus y minus n whole square equal to 0 is the equation of all possible circles of family of circles that are tangent to C1xy at the point m comma n. So basically what is happening is m comma n is the point at which you can think of m comma n as a single point, or you can think of it as a point circle, right? M comma n is a circle of radius 0. Circle of radius 0, the equation of this circle would be what? X minus m whole square plus y minus n whole square equal to 0. That is a circle of radius 0, or that is a point, right? Now we know that if you want the equation of family of circles that pass through the intersection points of two given circles, you will do C1 plus lambda C2 equal to 0, right? So actually C2 is this and C1 is the original circle. So when you do this, you get equation of family of circles that are tangent to this at this point, because the point circles are all touching here, right? So you can say that these two circles are tangent. So in general, this is a generalization of the first property that we saw, right? But you can use this result directly. If you want equation of all possible circles tangent to a given circle at a given point, you should use this form, right? So that will be useful in problems. Let's look at now families of central conics. Families of central conics. What are central conics? Conic sections that have a center, like say circle, ellipse, hyperbola. Parabola is not a central conic. The center of a parabola is at infinity, right? So families of central conics. So now what we will say here is when lambda and lambda u, the product of these two real numbers, lambda u is not equal to 0. Basically, when we are saying none of lambda or u is 0, and lambda and u are not both negative, they cannot both be negative, and none of them can be 0, then the standard equation of the family of central conics with center actually at 0 comma 0, with center 0 comma 0 is given by this equation: x square by lambda plus y square by mu equal to 1. So that is why we had to have these conditions here, right? And also that is why we can't say that can both be negative. If both are negative, then this can never be equal to 1, right? This is not a real curve then. However, if these two conditions are satisfied, this curve is always a central conic. It's either a circle, ellipse, or a hyperbola with the center at 0, 0, right? Here lambda and mu become our parameters, right? Now we look at some specific cases of these. So first of all, equation. Okay, I'll do this on the next screen. Equation of family of central conics with common foci is x square by m square minus lambda plus y square by n square minus lambda equal to 1, where m and n are constant and they are actually constant such that the semi-focal distance, which is typically the focal distance usually is 2AE. So semi-focal distance is AE is equal to actually root over m square minus n square mod of that. So m and n are those constants. The difference of their squares is actually half the distance between the foci of the curve, right? In this case here, lambda is a parameter. So this is the equation of all possible curves which share a common set of foci, right? The focus is common to two or more different curves. The general equation is given by this, right? Now, the second type that we will see is equation of family of conics with two common vertices. And this is x square by m square minus lambda plus y square by n square minus lambda equal to 1, where plus or minus a comma 0 are the fixed vertices. So the equation of the conics with common foci and common vertices is actually tending to be the same, right? The next one that we look at is this one, equation of family of ellipses with common eccentricity, with constant eccentricity E, right? Is this equation x square by a square plus y square by b square is equal to lambda. The lambda is a parameter. You can change the value of lambda and this equation represents infinite different ellipses, but all of these ellipses will have the same eccentricity, right? Similarly, equation of family of hyperbolas with common asymptotes will be basically x square by a square minus y square by b square is equal to lambda. This is the equation of the common asymptote hyperbola, right? And then finally, we look at the general form here, equation of family of conics that pass through the intersection points of two conics x square by a1 plus y square by b1 equal to 1, and x square by a2 plus y square by b2 equal to 1 is, you just do the standard thing that we have learned by now. We may write the equations of each conic plus lambda x square by a2 plus y square by b2 minus 1 equal to 0. Here lambda is a parameter and this is the equation of the family of conics that passes through these two conics intersection points, right? Okay, so once we have seen this theory, now we'll learn how to apply all of this to various problems. So let's look at some simple examples. The first one is find the equation of the circle that is tangent to x square plus y square minus 4x minus 8y plus 15 equal to 0 at a point P, which is 3 comma 6, and passes through another point Q, which is 5 comma 6. Okay, now we'll apply the principle here, family of circles rule. Now we want the equation of all possible circles that are tangent to this given circle at this point P, right? So at this point, we can write the point circle equation x minus 3 whole square plus y minus 6 whole square equal to 0. And the equation of the family from the theory that we have seen is p1xy plus lambda times x minus m whole square plus y minus n whole square equal to 0. So in this case, it will be x square plus y square minus 4x minus 8y plus 15 plus lambda times x minus 3 whole square plus y minus 6 whole square equal to 0. This is the equation of all possible circles that pass through, that are tangent to this circle at this point, but they also pass through 5 comma 6. So 5 comma 6 lies on this equation. So it satisfies this equation. If you put that in it, you will get the value of lambda to be minus 2. And after that, after a little bit of simplification, you will get the equation of the desired circle. You should check it out yourself. The desired circle will come out to be this. This is your final answer. So straightforward application of the theory that we have seen so far. So that should be pretty easy. Now let's look at another example. We have the ellipse x square plus 2y square minus 2 equal to 0, and the line x plus 2y minus 1 equal to 0 intersect at 2 points B and C. Given point A as 2 comma 2, find the equation of the circle that passes through the 3 points, passes through A, B, and C. So that is our question. So now think about it. This is an ellipse and the line is intersecting the ellipse at 2 points B and C. Now, what we know, the theory is in general, if you write this family of curves, lambda times this plus mu times this, right? This should be any curve like this, any curve of this family always passes through B and C, right? because you should realize that B and C were lying on the ellipse and also lying on the line. So they will definitely satisfy this equation, right? But any curve of this form always passes through B and C, but that doesn't mean this family doesn't contain all possible curves, all possible conic sections that pass through B and C, that pass through B and C. You need to make sure that you understand this sentence. So it is true that any curve with this equation will always pass through B and C, right? Because B and C lies on the ellipse also and on the line also. But it is not necessary that this equation represents all possible conic sections passing through B and C. There could be other conic sections that pass through B and C which don't follow this pattern, right? Which don't follow this equation. For example, there could be circles that pass through B and C. You could draw circles that go through B and C, but you will realize that any circle definitely doesn't follow this equation. Why? Because the coefficients of x square and y square are not the same. X square coefficient is lambda, y square coefficient is 2 lambda. So this doesn't represent circles, right? This could be other types of conics, but it's definitely not a circle. So we are missing all the circles that pass through B and C, right, from this equation, right? So therefore, we have to construct a slightly more general equation of a family of conics that covers all possible conics passing through B and C. We do that like this. We say lambda times x square plus 2y square minus 2 plus mu times x plus 2y minus 1. And we can write another line x minus 2y plus m equal to 0. Why are we putting this x minus 2y plus m? Because we want to make this general equation such that it always passes through B and C, passes through B and C, and also includes all possible conic sections through B and C. Conics through B and C, which means circles through B and C. Should have circles through B and C. How do I make sure that there are circles passing through B and C? This general equation, if you see, is such that the coefficient of x square and y square will turn out to be the same. The coefficient of x square is coming as lambda plus mu, and the coefficient of y square is 2 lambda, and here it is minus 4 mu, right? 2 lambda minus 4 mu. Now at least there is a chance that these two could be equal, right? So for it to be a circle, it will be, this should be equal to this, right? From where we can deduce that lambda is equal to 5 mu, right? So here we are generally trying to make it a general conic, and then we are checking that will it cover all circles? It will cover all circles if the coefficient of x square and y square are matching, right? So we will say lambda is 5 mu. So if we choose mu as 1, then lambda has to be 5, right? So if I put this one particular number here in this equation, I end up with this equation, 6x squared plus 6y squared plus m minus 1x plus 2 times m plus 1y minus m minus 10 equal to 0. And the question already told us that a which is 2 comma 2 lies on it. You should understand that this equation always will pass through B and C because this term will be 0 and this term will be 0. So the overall thing is 0. So it definitely passes through B and C. we are adding this line equation here just to make it such that it could represent a circle possibly, right? And when will it be a circle? When coefficient of x square and y square are matching, which means lambda is 5 mu. So if you choose lambda as 1, gamma will, mu as 1, gamma will be, lambda will be 5. And then this is the equation of the conic that we are getting. And since a to 2 comma 2 lies on it, if you put that here, we get the value of m as -8. So a possible equation of a circle that passes through ABC would be 6x square plus 6y square minus 9x minus 14y minus 2 equal to 0. And since we know that 3 points will always have a unique circle through it, and now we have found the circle equation, so this must be the circle passing through A, B, and C. So it's a tricky way to proceed, and you have to realize that at the end, we have by brute force gotten a circle equation by setting lambda plus mu is equal to this and all, and finding the value of m from here. And once you know one circle equation, it is guaranteed that there is no other circle equation that can pass through A, B, and C, right? So what is the general principle that we learn from here? So if you have two curves, which equations are f1 xy equal to 0 and f2 xy equal to 0, right? And these two curves have intersection points, right? Then the curve lambda 1 f1 xy plus mu f2 xy equal to 0 must pass through the intersection point, but this general equation may not cover all possible conic sections that pass through these points. So that is something that you must remember. So that is something that you must keep in mind, that this curve will pass through the intersection point, but it doesn't cover all possible curves like that, right? When two curves are conic sections and intersect at 4 points that are not collinear, the curve lambda f1 xy plus mu f2 xy equal to 0 can represent all conic sections that pass through these 4 points. So if there are 4 intersections of two conic sections, then the general equation will represent all possible conics that pass through them. But in general, if you don't know that these 4 points are there which are non-collinear, then you cannot make that case, right? So you have to be a little careful when you apply this principle, right? Let's go ahead and look at one more example, which will be actually a generalization of a theorem from plane geometry. Okay, so we have this question. Let Mn be a chord of a circle O and R be the midpoint of the chord MN, of chord MN. Draw two chords AB and CD at the point R, or through the point R, rather. I should write that instead. Now, a conic section that passes through A, B, C, and D intersects MN at P and Q. We have to prove that R is the midpoint of PQ. Okay, so let's try to understand what we are trying to do here. So MN is a chord of a circle O, and let's draw the figure here. There is a circle O, and let's draw a chord MN. Great. R is the midpoint of the chord, so this is my point R, and I will draw two chords through R. This is R, and one more chord like this. This is A, this is B, this is C, this is D. And we know that this is the midpoint of R is the midpoint of MN, right? A conic section that passes through ABCD intersects MN at P and Q. So it is possible that we can have a conic section that passes through A, B, C, and D, right? For example, you could have a hyperbola like this that passes through A, B, C, D. Let me draw it roughly like this. So in general, there could be many conics that pass through A, B, C, D, right? So the question is saying a conic section that passes through ABCD intersects MN at P and Q. So this conic section is intersecting MN line here at P and here at Q, right? We have to show that R is the midpoint of PQ as well, right? We knew earlier that R was the midpoint of MN. Now we have to show R is the midpoint of PQ, where P and Q are the intersection points of the conic that passes through ABCD with the line M, right? Okay. So what we can say here is the conic that passes through ABCD can be thought of as the family of conics passing through intersection point of the circle with lines AB and CD, right? We have already seen how to write the general equation in that case. So what we'll do is we'll set up the coordinate system and try to approach this in a systematic way, right? So here, what we will say is let R, I will just draw the figure here again. This is my figure. This is M, this is N, this was R, this was my AB, and this was CD. C, D, A, C. And my conic could be anything like this. right? This was P and this was Q. So let's say for now, let R be the origin. Be the origin. We are setting up our coordinate system and Mn to be the x-axis, right? Suppose the center of the circle will be, obviously center of the circle will be on this line. Center is O. Center is O, and O is given by the coordinates as 0, comma A. The coordinates of O is 0, comma A. A could be negative, right? Equation of the circle will be x square plus y minus A whole square is equal to R square, right? This is the equation of my circle. Equation of line AB can be given as, now AB and CD are both passing through my origin. My origin is R, which is 0, comma 0. So AB line can be written as y is equal to k1x, and CD line can be written as y is equal to k2x, right? So the combined equation of AB and CD, the pair of straight lines AB and CD, is y minus k1x multiplied by y minus k2x equal to 0, right? This is the combined equation of the pair of straight lines ABCD. So therefore, equation of family of conics that passes through the intersection point of my circle and these pair of straight lines should be this equation: lambda times y minus k1x into y minus k2x plus mu times x square plus y minus a whole square minus r square equal to 0, right? This is the combined equation of my conic section that passes through ABCD, right? From the theory that we have learned, we are applying that lambda times this plus mu times this. Since there are four points ABCD, 4 points of intersection, and none of them are collinear, therefore we can be guaranteed that this equation represents all possible conics through ABCD, right? So how do I find P and Q here? To find P and Q lie on my x-axis, right? So we can put y is equal to 0 in this equation to find P and Q. So let's put that y is equal to 0 here. So this becomes lambda k1 k2 x square plus mu x square. So I'll collect those terms together. Lambda k1 k2 x square plus mu times y is 0. So this becomes a square. It is mu times a square minus r square equal to 0, right? So what are we getting here? Think about it. This is the equation that should tell us the x coordinates of P and x coordinates of Q, right? Because we are trying to find where the conic section intersects our x-axis. So xp and xq are roots of this equation. And by Vieta's relation, we can see that xp plus xq is equal to 0. Because there is no x term here at all. So xp plus xq is equal to 0. And what does that tell us? Xp plus xq is equal to 0 means the midpoint of xp and xq is r, right? Because r was 0, comma 0. So therefore, midpoint of pq is r. Because we are getting xp plus xq is 0 and midpoint of pq would be xp plus xq by 2, which is meaning that the x coordinate of that would be r, right? So basically we have proved that midpoint of PQ is R, and all it took us is writing a general circle, writing two line equations, setting up our origin in the right way, in a convenient way. Otherwise, it would take a little more effort and time, right? And then just writing the family of conics equation, right? Actually, this is a generalization of a theorem in plane geometry that is known as the butterfly theorem. Butterfly theorem. So you should check out butterfly theorem, and now you'll see that we have proved it using conic section. So this is This can be a good exercise for you. Look at butterfly theorem online and see what we have proved. We have proved a generalization of the butterfly theorem. So those were some examples that should give you a taste of how you can apply the theory of family of curves to different coordinate geometry problems. Hope you have learned something from the video, and from the next class onwards, we'll get back to more standard Olympiad topics. The next video will be about mathematical induction. So look forward to the next one, and I'll see you next time.